Okay, this is a calorimetry problem that involves phase change. It's the toughest type of calorimetry problem that you're going to do. So here we go. So we have a sample of ice at 0 degrees Celsius, and we're given the mass, 100 grams, which is 0.1 kilograms. The initial temperature is 0, which is significant. So our ice starts here, right? I'm going to put a dot right there. The ice starts there, as opposed to ice down here. Now, what would be the difference? If you had ice below 0, any heat energy added to it is not going to cause a phase change yet. You know, any heat energy added would cause the temperature of the ice to rise, but it wouldn't cause a phase change. So ice at 0, any heat energy added to it is going to cause the ice to melt. Okay? Now, the water starts here, like up at 80 degrees Celsius. Water starts there. Now, when the ice gets dropped into the water, the ice is going to melt, which is going to cause the water to cool, and they're going to meet somewhere in the middle, right? And that's called the equilibrium temperature. So the equilibrium temperature, that's where the ice and the water meet, right? Now, how many steps must the ice go through to get to that equilibrium temperature? 2. So let's label this step A and step B, okay? How many steps does the water have to go through to get to that equilibrium temperature? Just 1. Let's call that step C. So the ice is going through A and B, whereas the water is just going through step C. Now, what's the main idea with calorimetry? The main idea with calorimetry is heat loss equals heat gain, right? Which object is losing heat in this problem? The water. So I'm calling the water object 2, and the ice is object 1. So we're going to say the heat lost by the water, so that's going to be negative Q2. Actually, let's label that QC for step C. Sorry, QC. That's the heat involved for step C. Why did I make it negative? Because it's losing. Is going to equal, now the ice gains heat in step A and step B. So this is going to be QA plus QB, where A, B, and C are the steps. Okay? All right. Now look, what I tell students is you can absolute value everything unless they're asking for the final temperature, unless they're asking for the equilibrium temperature, which is what's going on here. In this problem, they want us to solve for the final temperature, which is the equilibrium temperature. So we cannot absolute value. We got this negative right here is going to become important. Okay? So we're going to go negative M2 specific heat of water delta T. Now what's delta T? Change in anything, what's change? Final minus initial. So we're going to go temperature final minus 80, because that was the initial temperature of the water, equals, okay, now what's QA going to be? QA, what's the equation for that step? The equation for a phase change is ML, where that's M1, right? It's the mass of the ice, plus this B right here, step B, is going to be MC delta T. Change of temperature is always final minus initial. So that's going to be T final minus 0, right? Because the starting temperature was 0. All right, now we're going to have to distribute here, right? Now here's where this negative becomes important. So we're going to get negative M2 specific heat of water, temperature final, plus 80 times M2 specific heat of water equals M1 latent heat of fusion plus M1 specific heat of water T final. The only thing missing in that equation is temperature final. That's the only thing missing. Temperature final comes out as 65.5 degrees Celsius when you punch in. Okay?